Hey everybody, welcome back. My name is Jacob, and welcome to the third video in my Blockchain in Rust series. In this video, we're going to be going over actual chains of blocks, finally, and some verification checks that we can do on our blockchain to make it a little bit more secure. So here's my little introduction to the project slide. Get all these tools if you don't have them already. I have gone over this a little bit more in the videos beforehand if you've been following along. And you can get, as always, the code from this link right here. Okay, so we are going to make an actual blockchain, which, as it turns out, is just going to be a list of blocks that we store in a struct for now. But it gets cooler. So let's do that. Let's make our blockchain struct. This is the code as we left it in the last video. So I'm just going to create a new file here and call it blockchain.rs. Here we'll create our new blockchain struct blockchain. And it just has one field, blocks, and that'll be a vector of blocks like that. Of course, this file doesn't know what the heck blocks are, and also we haven't included it in our lib.rs file yet, so we'll just put that in there right now. Mod blockchain of use create blockchain. I'm trying to make sure I spell everything correctly. Alright, now this is going to be broken because it doesn't know where the heck block is, so we'll just say use super and everything, and that should fix everything for now. Alright, great. Obviously this is not a very interesting struct, so let's go over here and use it to make a chain of a bunch of blocks for us. So this is what we had in the last video, and I'm going to rip a couple of things out of here. We'll have our difficulty, because we'll set the same difficulty for all of our blocks in this example. So there's our difficulty. I'm actually going to make it a little bit easier so that the hash times, the run times don't take so long, and I can demo this a little bit quicker for y'all. So that'll be difficulty. And then I actually probably don't need that parameter there anymore now that we've written the mining function, but oh well, I'll leave it there because I'm lazy. So here is our Genesis block. We can remove this little bit of code, and so we'll just mine it. Let's say mined Genesis block, like that, wonderful. And then we'll create blockchain. There's all my typos. All right, and inside we'll have blocks, and that will just be a vector of, for right now, just our single Genesis block. Okay, now let's create a loop. I in 1 to 10. This little guy right here is going to give us a range, so we'll have values from starting at 1 and going through and including 10. That's what the equal sign does. Otherwise that would be 1 2 3 4 5 6 7 8 9. Now that makes it 10. Sweet. So here we'll just pretty much copy this and paste it in there. What will be different? This will be different. This will just be another block. This will be different. That will be I, because that's our index. And then we need to add it to our blockchain. So we'll do that by saying blockchain.blocks.push block. Sweet. There actually is another problem, and that is this is our previous block hash value, and obviously the previous block hash at this point in time when we're running through this loop is not all zeros. It would be, for the first iteration, it would be the Genesis blocks previous, or the Genesis blocks hash, and then it would carry on just lagging one behind. So what I'm going to do here is make a variable let mut last hash equal block.hash.clone, like that. And then that can go, oops, right here, last hash, and then we'll mine it and set last hash equal to block.hash.clone, like so. And now we should have, that will be lagging one behind, and so it'll always be the previous hash. So, oh, that's not Genesis block anymore. Let's run this and see what we get. All right, I did turn the difficulty down so it's not taking too long, which is good. And there we go. We got blocks 0 through 10, and we see the nonces here. It's been mining. There we go. Beautiful. All right, so that appears to be working, and we have a blockchain struct. Beautiful. All right. Now, if you remember back from the last video when we talked about mining, the mining process is essentially just like searching blindly for a key that suddenly unlocks, it fulfills the difficulty requirement. So you generate all these nonce bytes, just essentially brute forcing your way through, and eventually you find a combination of bytes that makes the hash of the block fulfill the difficulty that was set by the network, or in this case, it's just the difficulty that we've hard-coded beforehand. This mining problem is interesting because it's very difficult to solve, or you can make it very difficult to solve, but it's still extremely easy to validate your solution, like to verify your solution. So if someone says, hey, look, I mined this block, here's the nonce, you can say, okay, I'll just hash all these bytes together. Does it match the difficulty? Yes or no? And it's really easy. You don't have to go through and like search for a nonce again or something ridiculous like that, because that would take a lot of time. So it's a difficult problem to solve, but that you can verify very quickly. So that's what we're going to do. We're going to verify some of these. Well, we're going to verify a couple of the properties of the blocks that we have in our blockchain. The actual Bitcoin verification process is 19 steps long, and that involves a lot of verifying of transactions and other nifty stuff that we neither have the infrastructure nor the time to go over. So I just came up with 4 things that we can verify using the current code base right now. 4 things that we can verify, and those are verifying that the actual index, like where the block is going to be, like, so we'll receive a new block that we want to add to the end of our blockchain, and we need to check to make sure that the index it claims to be positioned at is the index where it actually is going to be positioned at. Hopefully that makes sense. Otherwise, I'll write it in the code. It'll be pretty straightforward. That's one of the simplest ones. The second thing is that we have to verify that any given block, when hashed, actually matches the difficulty it claims to match when it's hashed. We are going to be just blindly trusting the difficulty that is associated with any given block. So a block will come in, it says, hey, I fulfilled this difficulty. We'll say, okay, then verify that the hash fits that difficulty, but we won't verify that the difficulty is actually the correct difficulty, because we have, again, no infrastructure that says, all right, here's the algorithm for deciding how difficult, how high of a difficulty this block at this index or after this block or whatever should fulfill. So we'll just be trusting that. That is insecure, but now you know why. The third thing is we're going to be verifying that time is always increasing. This is a super simple, more naive version of what Bitcoin does, because Bitcoin is such a large network. You can't expect everyone's clocks to always be in sync with each other. And also there's network latency and other things that, well, to be perfectly honest, I don't understand everything about Bitcoin. So this is just a super oversimplified version of making sure that the timestamp isn't ridiculously out of whack. And then the fourth thing that we're going to be verifying is that the previous block hash that the block that we're verifying claims, like it says, this is the hash of the block that I immediately follow, then we'll make sure that it actually is correct. So it'll be in order in this list of blocks that we have, and we'll check to make sure that the previous hash it claims is the actual hash of the previous block. All right, so let's implement that blockchain verification function. This is where things are going to get a little more interesting, because we have this blockchain struct that has nothing in it, but we'll add a function and that will be fun. If I can type. So we'll write an implementation block for our blockchain, and we'll say public function verify. That will take self and it will return a boolean, and then we'll just loop through all of the blocks. So for now we'll do something kind of a funky trick here. Looks like this: in self.blocks.iter.enumerate, and this is going to give us the index and the block together in a tuple, which we can then destructure. I think that's the proper term, destructure, with this little piece of code right here. So we get the index and the block associated at that index, just a little bit more concise. Then, I mean, you could perfectly well just loop through the indices as well and grab whatever. But that's just what that does. Hey, there's a little bit of extra Rust education for you. All right, so our first thing is just checking that the indices match. This is super easy. If block.index is not equal I, there, it failed the test. So we'll say print line index mismatch. That sounds like a good error message. Not equal to that. Then we'll just pass in block.index and I, like so, and return false. Beautiful. All right, so there is, and we'll return true here because we'll just short circuit right here. If it fails a test, we'll just return false, so we can return true there. Not equal I. All right, this as U32 because that's an index, and wow. Okay, big deal. Not really. This is just like a typecast to a different type of integer that it will work just fine for all purposes. All right, so there's our first test. If the block index, or if the index that the block claims to be located at is not where it actually is located, it fails the test. All right, else, what is our second test? It would be matching difficulty. So else if not block check difficulty, right? This, we're looking at this function right here, check difficulty. It takes a hash and difficulty. Check difficulty takes a hash, so that would be block.hash. It's not block.hash without parentheses because we actually want to calculate the hash of all the bytes. For the purposes of the verify function, we're just going to be completely ignoring whatever is attached to the hash field, because we don't need to verify that. We can just check this guy against the difficulty. That's all that really matters. So check difficulty against block.difficulty. Again, ideally, we would also verify this value against some network provided like formula for generating the proper difficulty, but we're ignoring that. That's insecure, but you get the point. So then we'll say print line. Oh, this has to be borrowed. Sorry. Print line difficulty fail, and that's good enough. Return false. Okay, so now these last two are going to only apply, or there will be special cases for the Genesis block. So we'll say else. Else if I not equal to 0, let's say not Genesis block, otherwise Genesis block. Okay, so the Genesis block won't have a previous block. So we'll just say that the previous block hash value always has to be all zeros. And we won't have to check the time at all because there's no previous block to check the timestamp value against. So we'll just forget about that test for the Genesis block. So we'll say if block.hash or previous block hash does not equal vector that looks like this, 0, 32. Then we'll say print line Genesis block previous block hash invalid. Sure. Return false. And then so that's all we have to do here. And then for not Genesis blocks, we will verify that time increases. So if, well, okay, I'm going to say let previous block equal self.blocks I minus 1, and this will need to be borrowed like so. Haha. Okay, and then we'll check to say if block dot timestamp is greater than, is less than or equal to previous block dot timestamp, print line time did not increase. Okay, sure, that's good enough. Return false. And then here's our last verification check. Else if block dot previous block hash not equal to previous block dot hash. That should work. Yes. Print line hash mismatch. Return false. False. I can spell. All right. So there we go. That should be our entire verify function. Let's test it out. This will be fun. So I'm going to start and just make sure that it works for our Genesis block. And so I'll say print line verify like so, and we'll say blockchain.verify like that, and then return because I don't want to waste all that time. Please work, verify true. All right, sweet. Okay, so then we'll copy this and just paste it at the end of this guy every single time, and we'll see what happens after we mine each block. Oh, verify. Time did not increase. Right, because I am not actually, okay, these are all zeros. We can finally use our now function. That's what I was supposed to do. All right, time did not increase. Now time should increase. Verify, true. That looks good. All right, now let's make sure that we aren't just returning true all the time. And change some stuff here. So blockchain.blocks 3 dot, let's change the index equal to 4. Okay. Let's see if it breaks. True. Oh, come on, mine faster. All right, almost done. Okay, it says verify false, index mismatch. Perfect. Let's tinker with the hash a little bit. Let's change like the 8th or 9th value of the hash and just add 1 to it. That should break some stuff. True. Now we should get a hash mismatch. Beautiful. The other possibility, I guess, is that we could have gotten a doesn't match difficulty. I might have to change something else. Oh, yeah, I would have to forget I said anything. Okay, let's see, what else can we change here? Timestamp hash. We could play with the nonces, but that's no fun. We already did that. Let's change the payload. Payload equals, nope. dot to owned, like so. Verify that. True, 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 true. Looks good, looks good, looks good. And then all of a sudden difficulty fail because it hashes it all and it doesn't match the difficulty anymore. Okay, so let's see. We hit index mismatch, difficulty fail, time did not increase. We already figured out that worked. Hash mismatch. I can't speak. So if we change previous block hash, some value in here equals 8, because why not? Does that work? This is just my basic testing. This should work. Work, work, work. There, difficulty fail. Beautiful. All right, so that just about wraps up everything I had to say in this video. I certainly hope you enjoyed this tutorial and learned something. In the next video, or maybe in 2 videos, we should be finally adding transactions, the concept of transactions, to our blockchain. I hope you stick around till then. But otherwise, my name is Jacob, and have a good one.